When you have multiple resistors or multiple devices, you have a choice on how you wire them, on how you're going to have the electric current pass through them. And there's two overall classes that you need to learn about. They're called series and parallel circuits. So this video and the one that follows are going to try to distinguish between them and help you understand. This one will be series, the next one will be parallel. Broadly speaking, in a series, you have one thing that comes after another. A series of events is this happened, then that happened, then that happened. And that's what a series circuit is. Current leaves the battery, and it goes first through one resistor. There's nowhere else for it to go. It then goes through another, and another, and it eventually gets back to the battery. There's only one path for it to go. So usually we would not draw a circuit by trying to draw pictures of the items. We would draw a schematic, which you've learned about in a different video. That's the symbol for battery. These are the resistor symbols, and I color-coded them to match above. But again, current leaves, goes through one, then another, then another. We're going to try to learn about this kind of circuit and how it works. So I'm going to walk you through a series of lab experiments to determine how the two important variables we've seen in circuits, voltage, the energy per charge, and current, how fast charge is flowing, how they divide up in a series circuit. In this simple video, we're going to use three identical resistors. In the lab, you're going to do a more complicated one, and you're going to see how different resistors get different amounts of voltage and current. This is the circuit I want to investigate first using resistors. I have a 9-volt power supply. It's going to go through a 100 ohm resistor, then another 100 ohm, then another 100 ohm, back to the power supply. What we're interested in is both the voltage across a resistor and the current through the circuit. So as we discussed before, to measure the voltage across a resistor, I'm going to actually physically measure across it. I'll put a voltmeter like this over the first one. I'm then going to also measure current, and current actually has to be put into the circuit. We put the ammeter in the circuit. I'm going to put it right after the positive side of the battery. So I'll show you what the setup circuit looks like after I do that. So here's the setup circuit. I've got a voltmeter wired across this first resistor, as we can see in our schematic. And I've got an ammeter wired between the power supply and that first resistor. So if we look at this wire, it goes into this meter, and the other wire from the meter goes over to the power supply. So how do we come up with the total resistance? I think the easiest way to see this is to think about a traffic jam. So I've drawn a highway here, Interstate 40 through Oklahoma City. And if it's a particularly bad time of the year, there might be multiple construction zones here. So I-40 traffic flows pretty good until construction starts happening. And let's say we've got the massive construction zone here, west of the city in like Yukon, Bethany area. That's going to slow the flow of current down across the whole road. We might have backups all the way. What if they decided to put another construction zone over here? Well, that's going to slow it up more. And that's what we just did here. We had one construction zone, two. We put in a third, it's going to slow it up even more. So when you add resistors in series, it's actually really easy to calculate their total resistance. So the resistance in series is simply the resistance of the first one plus the resistance of the second one plus the resistance of the third one, and you just keep going, all the resistors you have. In the course of these videos, we're going to look at the voltage across the first resistor using this meter, and we're going to look at the current through the circuit using this meter. In this video, I use the analogy of traffic on the highway and construction zones as a reason why adding more resistors in series seems to slow down the current through a circuit, just like it would slow down traffic on a highway. So what I want to do now is see what that might look like experimentally. We're going to set up these three circuits, a 9-volt power supply with 1 resistor, with 2 resistors, and with 3. I currently have the 3 set up. And we're going to measure the current through the power supply here, and we're going to measure the voltage across one of the resistors. Because I used identical resistors, the voltage across all 3 will be the same, which I'll show you in just a second. But we're going to see what happens to the amount of energy per charge, the voltage, as we increase the number of resistors, and what happens to the electric current, the traffic, as we increase the number of resistors. I know I just am measuring the voltage across one resistor. Because I used identical resistors, the voltage will always be the same. So if you watch, I'll try the second resistor. The voltmeter went back to the same value of 3. I'll try the third. The voltmeter went back to the same value of 3. So just by monitoring one resistor with them all being identical, we get an acceptable value for all the resistors. Got my 1 resistor circuit here, and we could see that the current through the battery is 0.087. And my voltage is a little less than 9. I have my 2 resistor series circuit here. We could see that the current through the power supply is 0.044. And my voltage is about 4.5. So I've got my 3 resistors here. We can see the volt across each resistor is 3 of the total 9 volts. And the current through this power supply is 0.03. So I made a mistake when I wrote down the value for current with the 3 resistor circuit. As you can see for the multimeter, it's 0.03, which I said in the video. And I want you to pay attention to this pattern. With 1 resistor, we had 0.087. With 2, we had 0.044. With 3, we have 0.03. So that's where that traffic jam analogy becomes really helpful. Less current can get through the circuit the more resistors we've added, because we've added more traffic jams. The more resistance you have, the lower current you're going to get. So we're now going to look at what happens with voltage. Remember that current is how many charges get through. Voltage is how much energy each charge carries. So they're both pretty important for understanding how energy divides up in a circuit. There's something else that's interesting too. The energy per charge that each resistor gets seems to decrease. In this case, we have 9 for 1 resistor, we have 4.5 for 2, and we have 3 for 3. It's pretty obvious what's going on with that. This is 9 divided by 2, and this is 9 divided by 3. So we seem to be sharing the voltage in a series circuit. Let's look at why. So right now I have the voltmeter hooked up across this first resistor right here. And we can see, as before, it's measuring about 3 volts. Watch what happens when I leave its positive lead where it is on the left side of that first resistor. But then I go and put the negative on the end of the second resistor. It jumps up to 6 volts. And then if I have it go all the way to the end, it jumps up again, up to 9 volts. What's going on? Well, let's look at our circuit. The power supply takes a charge that starts here, and it gives it a certain potential energy per charge. If that's going to go all the way through the circuit and return to where it started, it's kind of like if you went on a hike. You park your car, you go up a mountain, you got to come back down. And what we were seeing was that all the potential energy each coulomb gained going up here was lost by the time we got back. Since these are 3 identical resistors, the amount of energy lost per resistor was the same. So we lost 3 joules per coulomb here, 3 joules per coulomb here, 3 joules per coulomb here. That's why we shared the voltage.